A few announcements. We're going to need to postpone the field trip. I don't have a good date yet. The reason, some of you've heard rumors, some of you have not. I've had a minor heart attack. It's a silent type, but about 5% damage, and a small microstroke that put me in the hospital for the weekend. And the date of the field trip, they're going to be doing a series of tests to try to figure it out. So I will not be available to do the field trip. Nothing to worry about. It's just a matter of getting old. These sorts of things happen. So no worries. Once we have results back from the tests and know what the next best steps are, then we'll try to find a good date for the field trip. I'm thinking going to be closer to November or closer to Thanksgiving holiday, a little bit cooler, and we might have to make some adjustments there. We need to start discussing and try to finish off on inversion. That will finish up our work on faults and fault systematics. We then will step into folding, and I just about have most of the notes cleaned up for folding and the slide presentations for folding. And once we get through folding, we will just briefly touch on foliations, fabrics, different types of lineations, foliations, features that your textbooks actually spends quite a bit of time on, because he's really more of what we term a metamorphic structural geologist. And since in this college we have a bit more of a emphasis on petroleum and petroleum related systems, we don't spend that much on metamorphic types of structural geology. And then after that, we will jump into the next phase, because remember, we've talked about from the beginning, when we think about the basic concepts of structural geology, we make statements like stress causes strain. We talk about the behavior of a material in terms of the imposed rate of strain versus the mechanistic rate of strain, the strain rate at which it can respond given the conditions. And so we need to step away from mostly descriptive into really starting to investigate some of the basis of mechanics. And so we're going to start off and do an overview or a review, depending on where you are, of stress, ending with the differential equations of equilibrium. Then we will touch on strain. Both of these are what we term second order tensor systems that has some unique mathematical properties, some beautiful mathematical properties, and end up with the differential equations of compatibility. And from that, we will step into and start asking questions about how do materials really behave, and go back and really look at some simple concepts of elasticity, plasticity, viscosity, and from there into what's happening in the material that allows it to behave in this way. And so we'll become a little bit more mechanical, a little bit more mathematical as we step into the mechanics. For some, that will be refreshing. For some, that will be a little bit more challenging. And we'll just try to work through and make sure we progress on task and on target. So we had a challenge last time, and I gave you a series of maps, a couple of maps, geologic map. One was the Hydrologic Atlas, which is a publication from the Oklahoma Geologic Survey that has not only the geology, the superficial geology, it will also talk about water quality and aquifer systems. And I gave you Circular 91, which has a slightly larger geologic map of the Arbuckle Uplift itself. That particular system is intriguing. Circular 91 is about the Arbuckle-Simpson Aquifer, which is a massive aquifer system in south central Oklahoma. The Arbuckle-Simpson Aquifer is a fractured and karstified aquifer. If you look at the Arbuckle Uplift proper, there is roughly 2,000 feet of fresh water there, subsurface, which has caused a lot of interest in terms of can it be produced, can it be utilized. There's some issues with that because if you start thinking about this as a reservoir, the total recoverable water from the system is actually rather low because it's a fractured reservoir. So the total porosity is on the order of maybe 5%. So if you have a 2,000-foot waterhead, but only 5% of that is water, you have minimal recovery from that particular system. So you were charged in working with groups to come up with an interpretation. What style of features do you see? Is this a thrust fault system? Is this a normal fault system? Is this a strike-slip fault system? So, who wants to go first with your interpretation? Which group? We had 7 groups that were working. Who wants to hazard a guess? Tim?
We saw a lot of thrust faulting occurring.
So we see in that system, you see thrust faults. Any other interpretations? Yeah.
Strike-slip faults.
Strike-slip faults. You see quite a few strike-slip faults. Do you see any evidence of normal faults? Yeah.
Yeah, most of the smaller faults were normal, like the little teeny tiny ones.
Okay. Anything else that we saw in there? Is there any evidence anywhere in that area? Remember, we had a horrible definition of what a strike-slip fault system should look like, where we had a mastomosing bifurcating fault system that gives us lateral juxtaposition of dissimilar lithologies. We talked about pull-apart basins where we would dump localized conglomerates. Do you see any evidence for any of those things? Yeah.
I think we saw, and I'm sorry, I don't have the map in front of me, I'm not sure which one it is, but we observed on the eastern portion of the map that there was what we expected to be, I'm pretty sure, a releasing bend system. And so you'd expect to get, with that negative flower, filling in something like that.
So you, and Mohammed, you were nodding your head too. You noticed a releasing bend. Did everybody pick up on that? So we see here bend. Did we see any folds?
Fold?
Folds.
Yeah, I thought I saw a fold.
So if we were to draw one of the major faults, we saw perhaps a little releasing bend in here, and we see a very large anticline plunging off of that feature. All right, the Arbuckle anticline, that particular anticline is roughly 12 kilometers across at its widest place. And we saw in that a releasing bend. So we see a plunging anticline. Did we see more than one? Yeah, there's quite a lot of folds in that particular area. You see the Arbuckle anticline, there's the Dwarfy anticline, which is this beautiful little anticline that's only a couple of kilometers across, but it extends for about 6 or 7 kilometers. Lengthwise, it's almost at the same orientation as that. Did you see any evidence of on echelon fault patterns? would you describe these faults as being in an on echelon arrangement? Yes, no? Who wants to break out their map? Can I steal somebody's map? Steve, can I swipe your map? Which, that one right there, thank you. So, if we look at this geometry, that is such a pretty map. Okay, so I will be Vanna White here. So we need an Alex Trebek. What's going on? If we look, we see a series of faults roughly cutting through at about that orientation. We see folds that are at an angle to that. We see a releasing bend. Would you dare say that you see any faults that appear to have a synthetic orientation versus faults that have an antithetic orientation? Yes? No? Maybe? Or did you find this fault, did you find this system to be confusing and complex? You vote for the latter. Sam votes for confusing and complex. If we look at the system, we have a series of faults with more or less a similar orientation cutting through here. They seem to truncate, they seem to terminate within the map itself. So that if we look at the pattern, we might be willing to say that we're seeing some evidence of on-echelon fault arrays. One of the keys of an on-echelon system, and Tim, you asked about this on your card, one of the characteristics of an on-echelon array is that when we have an on-echelon system, we see this sort of a piecewise offset character. They do not all have to have exactly the same orientation, but there's something unique about them. There's something unique about the on-echelon array because they tend to terminate so that the amount of displacement can vary significantly across the fault. From 0, where it terminates, to perhaps kilometers toward the middle. That's going to cause some of the folding, some of the small scale folding that we see in that particular system. And so if we look, we find what appears to be rather much an on-echelon array. And then the next question is, do we see any higher angle faults? Do we see, and I'll draw in see what these things look like. Do we see any faults that are cutting across like this in our system, which we might consider to be antithetic? And when we look at the map, I see a bunch of them cutting through here that are rather antithetic in nature. And as we start looking, you'll notice you saw some strike slip faults, you saw a bunch of faults that were identified as up and down. These faults, some of these appeared to have a left lateral type of dip.
Really quickly, I'm sorry, is this a left lateral?
Yes.
Okay.
So these should be right lateral and compressive at the same time. So if you had to take a vote, so we're going to vote on the arbos. And we're going to ask ourselves, is this strictly a thrust system? Is this a normal fault system? Is this a strike slip system? And we'll throw in vertical. So, which one would you check off?
Strike slope.
Or if we do the full physical geology, we can have some of the above, all of the above, A and B, C, D, and E, not F. How many choices do you get on those sorts of tests? So how many people would say this is purely thrust fault system? Okay, normal? Strike slip.
I'd be leaning more
So
towards
we're going to purity, or are we doing it all of the above?
I choose.
Okay, so do we need an all of the above?
Yes.
All right, so purely strike slip. Well, it's gonna change the vote, isn't it? Vertical block fall. All the above? Think so? All right. You're probably right. This system has been interpreted as purely a thrust fault system. It has been interpreted as initially seeing large-scale normal faults. Because there's something intriguing that happens. That information was not on this map, but if we look, the thickness, shame on you. If we look, the thickness of the Arbuckle group here is actually just a few hundred meters. When we get across the Ouachita Valley Fault down in here, it expands dramatically to almost 3,000 meters of thickness. So we've had a normal growth fault in that setting for the Arbuckle deposition. So people have interpreted normal faulting. We see significant elements of strike slip. We see the releasing bend. That releasing bend is this feature right there. That's where we see the Pennsylvania and Collins Ranch conglomerate accumulate in a normal fault bounded valley. So that's a pull apart. That's a little releasing bend right there. So we see evidence of a releasing bend. We see evidence of on echelon faults. The intriguing thing about the Arbuckles, and there have been multiple interpretations of the Arbuckles, most likely they are a transpressional strike slip fault system with significant inversion. And so it is kind of an all of the above. And so it has been deformed in a rather interesting and unique manner. So if you would, turn in your challenges, what you wrote up, and also please return your maps if you can.
Well, I don't think I can, you have my map.
Well, okay, but you have returned it.
Okay.
How is it that I now have 5 markers?
If you could just say your last name.
And I started with 4.
That's it.
It's a quantum problem. Okay. Now, did this exercise help? Did it cause you to think? Did it give you a headache?
It helped a little, but you were talking kind of fast and you like said it only once, so I missed a few, I did key words when you were talking.
Well,
You were mentioning that, these faults over here on the right, they drew, they can determine.
they
And
do.
you said so there is.
0 offset there,
Right.
and then your maximum offset is in here. The offset varies dramatically in that system.
Tak to charge. Sever.
That we're putting up?
Now, let me know if you have any questions.
You want me to fold this up or?
I'll get it.
Okay, go to the next one, so I just.
Like this is what we covers.
On this particular challenge, yes.
You mentioned the word inversion to describe the system. Can you go into
We're,
detail?
that's the discussion for today. So it was a setup. The concept of inversion is really the next topic that we need to think about. Remember, we talked about thrust systems. I guess I shouldn't have erased that. We've talked about normal fault systems. We've talked about vertical uplift. We've talked about strike slip. And in each case, what we've realized is that the systems in and of themselves can be much more complex than the simple stick diagrams that we had in physical geology. Now, please keep in mind, even though we're covering a significant amount of information, we're just barely scratching the surface of each. In the graduate level class, the regional tectonics class, we've spent, this is week 5 or 6?
6.
6. We spent 5 weeks on just thrust faults. And we had a consensus on Wednesday that we don't understand them very well at all. So, these things are actually quite beautiful in their complexity and in the nuances of how these particular systems develop and how they will behave over time. The next step, what we want to do is we want to look at the concept of inversion. And, I need to step back. Each one of these, because Yakin asked a very, very good question about whether these systems have distinct petroleum systems. Because we talked a lot about the petroleum system in thrust faults. Normal fault systems, rift-related systems, will have a very characteristic petroleum system associated with the thermal and subsidence history of that particular rift. A petroleum system is going to depend on what is the subsidence history, what sediments are available in the system, what kerogens are available in a system, what is the pressure, temperature, time relationship for that system. So when we think about a petroleum system, and we'll put this over here, I'm going to label it PSS, Petroleum System Science. We're going to think about what sort of basin. And in this case, these will be basins associated with the fault geometries. So in a thrust, it's the Foreland Basin. What is the sediment supply? And the burial history. What types of kerogens do we have available to the system? Are we dealing with plant material? Are we dealing with microscopic materials? What sorts of kerogens can we have? When we start thinking about the burial history, we want to think about pressure, temperature, time. That's supposed to be a small t, not an epsilon. So each of these will have a very unique petroleum system. They may have different kerogen types that will give you different types of hydrocarbons. And we generally realize that there are 3 dominant types of hydrocarbons when you look at the mass spec signature. When you take a hydrocarbon and run it through a GCMS, gas chromatograph, mass spectrometer, you will see different patterns in the carbon numbers from C4 out to about C30. And so each one of the kerogens will produce different sort of signatures. Different burial histories will produce different sort of signatures. And so each one of these is going to have a very unique petroleum system associated with it. And there's actually a graduate level course that we're offering right now just on that, petroleum system science. And how do you recognize different types of systems, different source terrains, different types of maturation processes that will have led to a particular accumulation of hydrocarbons in that system. This is dominantly thinking about conventionals, but it runs into unconventional plays. An unconventional play would have a similar sort of thing, except we're not concerned about whether the hydrocarbon was expulsed, because it's still trapped in its own source rock. And so you have some unique differences and some unique effects. So let's go back to inversion. The concept of inversion is where we take a fault and reactivate. Basically, we take an existing fault and we're going to reactivate it in the opposite sense of displacement. This is not a new idea. This is something that geologists have been discussing and thinking about for a very long time in the literature. It wasn't until the 1980s, however, where there was a classic paper written by A.W.B. Bally in a French journal, in French, so you have to read it in the French, where he suggested that there would be specific types of inversion that were feasible, and he pointed out that the North Sea had some very diagnostic styles of inversion, where we had a normal fault become a thrust fault in that system. And so the idea here, this suggests that all faults can be reactivated in the opposite sense of displacement. Typically, when we talk about inversion now, we're going to limit our discussion to normal fault systems that are reactivated in contraction. And so this has boiled down to normal fault in a contractional mode. Now, it doesn't have to be purely compression. It's not that we extend and then recompress. We could have transpression. And the Arbuckle system is actually a left lateral transpressional inversion system at the edge of a rift basin. And so it's a kind of unique and beautiful system that way. So we want to go through some of the structures that might develop when we have that type of system. And so we're going to start off with a simple diagram. I'm going to have a normal fault. It's listerine in nature. And for our purposes, at least right now, we're going to consider it to be relatively large scale. It may not be a completely crustal scale system, but it is a relatively large normal fault. So as the fault develops, what we're going to do, I'm going to look at a single block, keeping in mind that there should be more than one block out here. So I'm going to abbreviate. So here, that is the symbol for Unseweiter, German, and so on. In this particular case, you will have more than one block out here. What's going to happen in the way that we think about inversion, and this is a little bit stilted, but it is a summary of a series of papers that have been written on the topic. As this begins, what we think we see is initially what we're going to call a pre-rift sequence. Those are just sediments that were laid down prior to the normal fault being activated. As we progress, this block will tend to move downward and have active sedimentation. Okay? And of course, we have our Umsavita here. So that we find this geometry, this is our pre, and now we're going to deposit a section of syn rift materials. This is in a growth fault style of setting. Okay, we're good so far? So that we can develop a relatively thick, depending on the rate of offset, depending on the rate of subsidence, depending on the rate of deposition, we could end up with a fairly thick accumulation of syn rift materials. The style of this wedge, the thickness of the wedge, is going to depend on how quickly are things moving downward. How quickly are we depositing material? If we have adequate deposition, then this will continue to accumulate. If we don't have an adequate rate of deposition, we will develop a deep water system here. We won't fill it up with sediment. That goes back to the concept that Dr. Kerr talks about in accommodation space. How much room do we have? How much sediment do we have coming into the system? And so let's assume that all things are nice, so that we have a nice constant rate of subsidence, a relatively nice constant rate of sedimentation, so that we develop a thick syn rift system. Now, at some point, subsidence is going to stop. We're simply going to quit having this block move downward. Either we would shift our offset into a different block out here, or our rift has stopped spreading. And so we just simply stop. We stop subsiding. At that point, then what we would see, let's say the block gets all the way down to here. So here's our pre-rift system. It's been offset. This is our syn rift system here. So this fault is actually propagating upward, but it has the sense of normal displacement. And then on top, we put a layer of post-rift sediment. So again, I need my Umsavita. And this is pre. So we end up with this type of a geometry. Stepping down into our basin, we've now stopped motion on this. And if we examine this system and we interrogate the system and ask it questions, we find out that the pre-rift sediments are in a normal type of displacement. Our syn rift sediments are all in a normal type of displacement, and that fault probably has propagated up to an active surface. Our post-rift sediments don't show any offset at all. If we saw just that, we would say, okay, perfect, this is a rift valley system. It is a clastic wedge that we see, or some sort of a wedge, and so we would begin an exploration program to look at the up-dip side here to see if we might have any potential traps in that particular system. Now, what would happen if we started to squeeze this back together?
Uplift.
Yeah. The thing that we find happening is that as we take this from the extensional domain into the contractional domain, we start to reactivate that fault as a reverse fault. Okay? So what will happen is this block, which was down here, is going to displace upwards. So that we're going to move that block, let's move it back up to this level. So this is our pre-rift, and if we look at the geometry in our pre-rift system, it's still normal. So if we examine only the pre-rift materials, we say this is a normal fault. Life's good, let's move on. But what's happened? We've moved this block from here up. Oh, no, that's not red. We've moved it back up to there. We have that much reverse displacement. So what's going to happen is, in the simplest case, remember our sin rift stayed relatively thin over here. So our sin rift sediments are going to come in. Now we have a room problem. Things are going to have to be pushed up. So we end up with this type of feature. Our post rift will get bent out. This is our post, this is our sin, this is our pre, and we will end up with a large welt there, depending on how far this block has come up. The size of the welt will vary. We call this feature a rollover anticline. And that may extend on out into the basement or into the associated basin out here. The characteristics of a rollover anticline is that they are asymmetric. Shallow dips on the basinal side here, relatively steep dips on the marginal side. Does that make sense?
Could you repeat that, Dr. T?
So in this case, this rollover anticline will have shallow dips out into the basin, depending on whether any of these blocks have been reactivated. Steep dips here on the marginal side, on the side that did not see the deposition of, or the thick accumulation of sin rift materials. So again, these are pre, that's my sin, this is our post. So we can see the rollover anticline develop. The amount of relative offset will dictate the size of the rollover anticline. The amount of sin rift material will dictate the size of the rollover anticline. So it might be a relatively small feature, it might be relatively large in character, but it will be asymmetric here. If we continue to deform, a couple of things can happen. If we start thinking about it and we start thinking about things that we were considering back in thrust faults, we're doing work here. And work requires a significant amount of energy input into the system because we're moving a lot of material vertically. So a couple of things can happen. We can take this system here and propagate thrust faults out in front. So we can end up with a system that has this geometry, so that we're taking thrusting, a rollover anticline is here, this has come back up and we've actually put those little thrust faults out in front because we didn't have enough energy to lift everything up, and it was easier to propagate out these small scale thrusts. This is called a footwall shortcut. And you may have or may have not noticed, in the Arbuckle system, there's evidence of a footwall shortcut in the northern and western part of the map system. A series of little low-angle thrust faults out in front. We can also, if we get this thing inverted, where we try to push everything all the way back up or even higher, we can end up with, and I'm going to simplify the diagram a little bit. Let's say that we push it all the way back up to there. So our rollover anticline comes in and we oversteep it. So that what can happen is we can propagate out back thrusts in that particular system. So that these are called, those are into the basin. We've pushed up too high, just like we had in the vertical uplifts where Urslev talked about a back thrust coming off. We've come up too high. This can't stay that high, and so it relaxes and thrusts back out into the basin itself. You have some unusual things happening in these systems. A lot of times this can become a thrust fault out on the edge here. So let me put that in green. So we can have a high angle thrust fault out in front. We can have these back thrusts out in front, or these footwall shortcuts out in front, and we can have these back thrusts coming back out of the system. Yeah,
The back thrust, they are thrusting.
they are true thrust faults, but they're
Okay.
local. They're localized relative to that rollover anticline, and typically don't extend beyond that. And so you have these sort of odd floating systems that might be bounded on all sides by thrust faults, where you have this large asymmetric anticline in the middle of that particular system. We have, if we start examining this, we have some interesting things, some concepts that can be a little bit confusing. Because if we look in here, what's the configuration of the pre-rift? It's still in a normal fault configuration. What's the configuration of the syn rift? It's in a reverse or thrust fault configuration. So we can have both normal faults and thrust faults in that inversion system, depending on where we cut the system down to. So that we can move from a normal fault to a reverse fault along the same fault plane and go through a point where there's no displacement at all. Yeah,
Wait, so you said that the post would be a normal.
that's in a reverse post.
Okay, and the neutron was normal?
Pre is normal. Pre is in a normal offset configuration. So as we look at inversion systems, the magnitude of the faulting is going to depend on what's the scale of our system. If we think back to when we were talking about places like the Bighorn Uplift, the Owl Creeks, the Wind River Range, those are apparently large-scale inversion systems where they may be 40 kilometers across. And you may have a vertical uplift in the order of 10,000 meters or more. on those. Or they might be relatively smaller scale, like this particular system here may be. So these are the features. The characteristics are that you see both normal and reverse offsets. You see a large asymmetric anticline. You may see thrusting out in front. You may see back thrusting out into the basin. If you go along the trend of the fault, that may vary. You may have some areas that look like this. As we extend this way, you might have something that looks like this. If you extend further, you might end up with back thrusts. So you can end up with a system that looks like an all of the above. And just as a final thought to really make your weekend complete, is you don't have to have this as purely contractional. Imagine, if you will, let's play this video in our minds. Let's have an extensional rift. We're going to subside our normal fault. Now we're going to subject it to a transpression. Strike slip and compression. So we see a transpressional, contractional reactivation and inversion in strike slip. So we can see a left lateral transpressional inversion system. This little map is one of those. And all of the above. So you were right, Tim.
I'm sorry, what's the difference between contraction and compression then?
Contraction and compression, when I think of compression, if I said that this was reactivated in compression, I'm thinking that it extended and that I compressed it along the same axis.
Okay.
When I think about contraction, that simply means I'm shortening it somehow. But in this case, let's think about extending that thing out and then contracting it in transpression. So again, we would see strike slip features, we would see normal fault features, we would see reverse and thrust fault features, antithetic and synthetic faults, plunging anticlines, the whole 9 yards. It's a mess, and it's a beautiful mess. And it's a fabulous thing to think about and ponder over the system, because that may be what's happening here in that particular system. And that may continue on into, because in this system right here, we're at Eola Robertson Field, which had a grad student, Derry Keelig, work on. Derry did a beautiful job that interpreted as a transpressional pop-up feature that gets out into the Chauveltum, and I've had several students work out in the Chauveltum area. Again, all of them coming to a conclusion of transpressional contraction, which gives us a suite of very interesting structures and fields out here. Okay, so we're basically done with folds. I got folds on the brain. We're basically done with faults. Our next step will be as a foray into folds and fold systematics. I will have the notes. They should appear later on today. I think they're supposed to appear at noon. Still finishing off the slide set for those. The exams, I've read through them now twice, and I'm ready to start marking. So I should have those back to you hopefully Monday on that particular system. Just to let you know, the way I like to grade the exams is I like to read through them at least once, preferably twice, without marking on them, just to try to get them into my head, see what you're thinking, see how you put things together, and then I will start making marks and determine what the total percentage ought to be on each individual question. And so hopefully that'll get done over the weekend. All right, have a great weekend.
Are you guys